Hello, good morning or good afternoon. My name is Jon Brookshire. I am the Technical Director of the Integrated Systems Group at Latent AI, and today I'm happy to share our results of describing efficient operation of deep learning for in-orbit inference. I thought I would start by describing the assumptions we have about the environment that the satellites operate in. So describe a few of the environmental characteristics and then describe the implications and what they mean for our mission and our motivation for looking at deep learning efficiencies. So in terms of the environment, satellites are size, weight, and power or SWaP constrained. The satellite hardware is fixed after launch. We won't be upgrading, for the most part, the satellite once it's in orbit. The upload and download bandwidth is often limited. We have a narrow window in which to push information up to the satellite or bring it back down. And the time on target is limited, and the target set is evolving. That is to say, the satellite is, of course, moving. The target may be moving, so there may be a limited window to observe them. And the target set is evolving, so not just moving, but it may be changing over time. The mission and what we're trying to do with the satellite is changing during its lifetime. So in terms of implications, first, there's either a desire or a need to do onboard deep learning processing. There's been obviously a lot of positive results with deep learning. We'd like to apply those in the satellite domain. For example, we might like to retask the satellite quickly to make additional observations of opportunistic targets. We may also want to discard unneeded imagery and save download bandwidth. So for example, if we scan over an area and see that it's entirely cloud cover, there may be no reason to download that, and we can simply discard the data right there. Second, we'd like to be able to do deep learning inference efficiently on the limited hardware. So satellites once launched are not going to be upgraded. CPU-only operation is commonplace. We may have GPUs, for example, a Jetson or smaller class GPU, but we're not going to have a server-grade GPU that we might like to have. This could be because the hardware is simply old and the satellite has been up in orbit for some time, or it could be that the older hardware was chosen for radiation issues. Second, we need to do deep learning inference accurately. So there's a high cost if we discard data that we should not have or retask the satellite incorrectly. It can be difficult, if not impossible, to recover it. And then finally, we may need to update the models after they've already been deployed. So we might retrain the model on the ground, and then we want to send the updated model up. And so we want that file size to be as small as possible. So I'll talk then a little bit about how we're approaching some of these challenges. First, we're going to apply post-training quantization to optimize the models. We're going to compile the model to machine code, and then we're going to leverage quantization efficiencies during upload. So for post-training quantization, what we're going to try and do is map the data from whatever floating point representation it was trained in, let's say float 32, down to a representation that can execute more quickly on the hardware, for example, int8. And in doing so, realize space savings as well as leverage vectorized instructions capability. I'll talk today primarily about going from float 32 to int8 because that's the particular use case we see quite often. But there's nothing special about float 32. It could be in float 64, and there's nothing special about int8. It could be floating point 16. It could be int4 or int2. I'll talk about some of our results showing an order of magnitude reductions in energy usage, increases in inference speed while maintaining the accuracy. We also compile the model to machine code, so we try to avoid the use of interpreted models, things like PyTorch or TensorFlow, and actually cross-compile for various hardware targets, anything from legacy CPUs down to the latest GPUs. And an added advantage is because we are compiling an executable, we generally see reduced dependencies, which is convenient when we go to upload these models, let's say on an in-orbit system. I think it's pretty clear that when we go from float 32 to int8, there's a 4 times speed savings when we size savings when we do that. That's just a change in the number of bits. What we'll also show is some additional results we see that after quantization, when you're computing difference files, we get an additional improvement because we reduced the updated parameters that need to be changed substantially on the order of magnitude. Let me say just a few words about Latent AI. So we're a US-based startup. We are a spin-out of SRI International, founded in 2018. Our co-founders worked on the technologies that I'll talk about here today as part of some DARPA research programs they did while at SRI. Our product is called LEAP. It optimizes and secures AI models. And I am the technical director of the Integrated Systems Group, and what we look at is applying the LEAP toolkit to particular applications, in this case, a satellite update capability. So I reviewed the problem statement. I talked a little bit about our approach. I'll go into some more details about the approach in a minute. I'll then share our inference efficiency results as well as some of our upload bandwidth results. The first thing I wanted to do was review post-training quantization a little bit. So I'll make the observations. First, int8 representations require less storage than float32, exactly 4 times less storage. Also, int8 operations can often be vectorized and be faster than float32. So again, it depends on the particular hardware. You might want to use int4, you might want to use floating point 16. But in any event, the idea here is to convert models that use the floating point representation, in this case float32, to something that executes more efficiently on the hardware, in this case int8, and then reap those speed improvements and storage reductions that come along with that. The challenge, of course, is that int8 has a smaller range than float32, and the int8 operations also require different operators than the float32. So our task is to figure out how to map those operators between the two representations and data. So in order to do this, we use post-training quantization. The way we do it is we run the float32 model. We feed in a representative data set or a calibration data set. And at each layer in the model, we look at the activations and collect statistics. We then use those statistics to map from the float32 representation down to the int8. We can do that mapping in a number of different ways. I've listed 3 of them here. One is min-max, where we take the minimum and maximum and map that to the range of the int8. That can often be sensitive to outliers. We can do the average, so where we take the average of the min and the max across the calibration data set and map that to the range in the int8. We can also do normal, where we fit a normal curve to the data, look some number of standard deviations out, and map that to the range of the int8. Regardless of how you do it, we then map the operators and then go through and evaluate the results and determine how much change has been made. Post-training quantization, though, is just one step of the entire process. So what I wanted to talk about here was the entire flow from training data to the eventual binary that gets deployed on the satellite. So we'll start with application data. In this case, we were looking at computer vision data, so images, but the process is the same for 3D, audio, speech, biometric time series data. At the end of the day, it's just a tensor, and we're collecting statistics on that tensor. That information goes into LEAP train. Here we can pull from a model catalog, and the advantage there of using the model catalog is that for all the models in there, we have associated run times, power usage, and RAM usage for the eventual hardware that we're going to be deployed on. So we know before we've even done training how fast our model is going to run and how much energy it's going to use on the target satellite system. What we get out of there is a trained model. If you don't want to go through that flow, we recognize that some folks also have pre-trained models, let's say in TensorFlow or PyTorch. Those can be brought in there. There's nothing special about the output format for the trained model. The stage down there at the bottom center is LEAP optimization. This is where we perform the post-training quantization. That then gets moved to LEAP compile. LEAP compile actually converts the model into a machine code. So literally a shared object or dynamic library. It's a cross-compile operation, so we can cross-compile for ARM, Intel, NVIDIA. Our general approach is to use the best in breed in terms of underlying tools. We've also found that specific vendors will have the best libraries for their particular hardware. TensorRT for NVIDIA, Qualcomm has custom DL libraries, TVM and LLVM are all some of the tools we used in this particular case. What we then output is a shared object library that is the Latent AI runtime engine. And it supports security, encryption, and authentication, as well as distributed inference and several other capabilities. But what I'm going to talk about here today is the lifecycle management, so the ability to upload the model after it's been deployed. And here we ran several different models through the optimize and compile stages, and then examined the performance on NVIDIA Jetson devices, the AGX and the NX, as well as a laptop RTX 3060 from NVIDIA. Looking at the table here, we looked at a few different models: ResNet, YOLO v2, EfficientNet, CovNet, and YOLO v5. We measured the mean inference time, the peak total RAM, the energy per inference, and then the change in accuracy after quantization. And here we are comparing the original Onyx Float 32 to the optimized int8 model. So Onyx is a common optimized deployed runtime in Float 32, and then we're comparing that to the Leap optimized int8. In terms of the mean inference time, we saw improvements between 2 to 10 times. Peak total RAM usage in some cases was unchanged. We did find that TensorRT does use quite a bit of RAM, but it was anywhere from unchanged to maybe a 10 or 30% savings in RAM. The energy per inference could be anywhere from 10% to 96%, and the change in accuracy was about 3 percentage points. And here we set up the system to try and meet that target of maintaining the accuracy within 0.03. There are also cases where we want to keep the accuracy exactly the same. In that case, for example, we could compile for Float 32 and actually skip the optimization step altogether. Although you don't get the same mean inference time improvements, it does maintain the accuracy exactly. So PTQ is important to improve efficiency, but eventually you're going to need to update the model. And PTQ can also help improve the upload data rate. So in general, uploading a new deep learning model is similar to uploading any new set of files. So we have model parameters, let's say in Float 32, have a model architecture, so the backbone of the model, and then any supporting binaries that go along with it. For example, the version of PyTorch or any of its dependencies. And we have to send all of these files up to the satellite, and we can use tools like rsync or any patch-based distribution system. But there are many times when we are only fine-tuning a model. We don't need to upload the entire model. So in this example here, I'm imagining we have a satellite that's perhaps tasked with land use measurement. Before and after the 7.8 magnitude earthquake in Turkey, we might have been interested afterwards at looking at tent encampments or maybe damaged buildings. So we might retrain on the ground and then want to upload a new model to the satellite. So in that case, we only really need to send the parameters up to the deployed system. And it's clear if we're sending Float 32 versus int8 and are only sending the parameters, we're going to see about a 4 times speed up there. So that's one advantage of the quantization, is simply we have a smaller representation, we'll have less data to send. But we actually observed an additional benefit. And during fine-tuning, when you're using a Float 32 representation, nearly every parameter will change, at least in some small amount. But after quantization, a lot of those irrelevant small changes are done away with. So while the Float 32 value may have changed, and they all may need to be updated, after quantization, a lot fewer of the int8 values need to be updated. So instead of sending every parameter, maybe we only need to send a few parameters. And indeed, we found that to be the case in this particular work. So here we were using a YOLO v5 small model. In the first row, as expected, when we switched from Float 32 to int8, we got about a 4 times speed up. It's a little bit better than 4 times because some of the additional glue code and management could be eliminated with the smaller data size. When we then looked at the fine tuning, and in this case, we're updating the YOLO v5 small with 1 epoch of fine tuning to increase the performance a little bit. We found about 11 times speed up. And again, the difference there is that not every change made in the float 32 was actually important to the final accuracy. So after quantization, those irrelevant changes had been discarded, and we only need to update the changed in-date weights. Here, by the way, we were using rsync to compute a difference, and then applying that patch file after it had been transmitted up to the satellite. So in conclusion, we've demonstrated an order of magnitude energy savings after quantization without sacrificing accuracy. We've demonstrated the ability to target multiple platforms, Intel, ARM, and CUDA, and we've demonstrated the possibility of an order of magnitude bandwidth savings in terms of uploading a fine-tuned model. So clearly energy savings are important on a deployed system. You want to make the most use of the energy you have. You can use the extra energy to either run for longer, extend your mission time, or use it to run additional payloads and extend your mission capability. The ability to target different kinds of hardware is important. We're not going to be able to change, in many cases, the hardware after it's deployed. And in terms of the bandwidth savings, that's really going to depend on the particular model, as well as how much fine-tuning was done. We showed in this particular case, we were able to get about an 11 times speed up, but that'll depend on the particulars of how much fine-tuning was done and the size of the model. We have a lot of other capabilities that I'm not going to cover today, including support for security, watermarking, out-of-distribution monitoring, and deciding when the retraining needs to happen. I talked a lot today about post-training quantization, training-aware quantization, where you actually consider quantization during the training process, can also be important. Thank you.